Ignition sequence start. 6, 5, 4, 3, 2, 1, 0.
Hi, and welcome to Ignition Sequence. I'm John Murphy, and on today's podcast, we'll be diving into humanity's oldest and most profound questions. Where does life come from? Where is life going? And perhaps the most tantalizing of all, are we alone? Joining us to tackle these questions is Dr. Lynn Rothschild, an evolutionary biologist and astrobiologist at the NASA Ames Research Center. Lynn's work has taken her from the lab to some of Earth's most extreme environments as she explores the boundaries of life and its potential beyond our own planet. Her groundbreaking research in synthetic biology and astrobiology is helping redefine our understanding of what life is and where it might exist. In this episode, Lynn will share her journey from studying extremophiles here on Earth to creating synthetic organisms that push the limits of life. Together, we'll explore the origins of life, the potential for discovering life beyond Earth, and the astounding future that biology and technology could bring. Dr. Rothschild, it's really an honor to have you on the podcast. So, astrobiology. Astro meaning space, biology meaning the study of life. Tell us, give us a little insight. What is really astrobiology?
Well, I think that it really boils down to three sound bites that we came up with when the program started at the end of the 90s. And that is, where do we come from? Not just, I come from Connecticut or something silly like that. I mean, coming from Connecticut obviously is not silly, but it's not in a trivial sense, but where do we as life on Earth come from? So how did you go from the origin of life to this incredible diversity we have today? But even beyond that, how do you end up with a habitable body in the solar system? How do you end up with a solar system to begin with? How do you start at the very beginning where the elements that are needed for life are formed? So I believe that this question can go all the way back to the Big Bang and maybe beyond if there is such a thing. So the where do we come from, it means life. Where does life come from? And it's a very broad, to me, very liberating question as a biologist. Then there's the flip side. Where are we going? Now, again, it's not something trivial like I'm going downtown this afternoon or something like that. But where are we going in the future? Perhaps as a species, is our future off planet? But I think it really, to a large extent, is the flip side of the where do we come from? Because just because we are here, as humans are here, doesn't mean that the sun isn't continuing to burn hotter and hotter. And therefore, the habitability of planet Earth is going to change over time. And in fact, ultimately, the sun's going to go supernova and all that sort of stuff. And ultimately, the Andromeda strain in the Milky Way, the galaxies are going to merge. I mean, there are going to be all sorts of things that are going to happen unless we have incredible powers and technology to be able to reverse some of these things. And I actually think that we may at some point. So what's going to happen in the future in a planetary environmental context? And then the third question, which is the one that a lot of people, I think, see as synonymous with astrobiology, and that is the question, are we alone? And obviously, that's the one that really intrigues a lot of people, but it doesn't exist in isolation. You can't begin to understand whether we're alone or not unless you understand the where do we come from aspect. And the where are we going aspect, oddly enough, is the most important one because it's our future, short of little green men showing up on the lawn tonight. So I think that all three of them actually are incredibly important questions, and they really speak to us not just as a scientist, but as humans. So I've been arguing for years that these are some of humanity's oldest questions. Obviously, the first ones are, what's for dinner and how do I make a baby? But once you get beyond sort of the basic, you're eating and reproducing, we have good historical records of our ancestors from several thousand years ago looking up into the sky and wondering if they're alone and looking at this diversity around them and trying to understand the natural world. And of course, as part of that, understanding what's going to happen in the future. So I really do think that the big questions of astrobiology really speak to something that is a really fundamental need and interest to us as human beings.
Talking about beginnings, what's your beginning? How did you get started and pulled into this?
Well, there's sort of there's 2 or 3 things. Um, when I was 8 years old, I was in 3rd grade, like many people are when they're 8 years old, and we did a couple of days looking through a microscope, and I remember very clearly we looked at, human hair and onion skin, and on the 3rd day, I saw an amoeba, and that was it. I fell in love and wanted to become a protozoologist. Now, I've heard from a lot of my astronomer friends, they had similar sorts of experiences, but instead of looking through a microscope, they looked through a telescope. And there really is something about looking through either a microscope or a telescope. You're being privileged to enter this world that is devoid of other human beings. It's absolutely real and sort of fantastic at the same time. And so I really wanted to be a protozoologist, and then got very interested in algae as well, and particularly evolutionary aspects, something that I realized was sort of fundamental to my interests during my undergraduate career at Yale, which has been very, very strong in evolutionary biology for many, many years. And then I went off to grad school and took a class on molecular mechanisms in evolution and got very interested in the revolution that were going on in molecular biology and how that can help to answer some of these fundamental questions. And somehow, at some point, I got recruited for a postdoc at NASA. And so that was an interesting experience because it was the end of the '80s. It was post Viking, where we had had the finest minds on planet Earth, certainly within the United States, really tackle that question: how do we look for life on Mars? And it's very popular to make fun of the Viking approaches. And I am in their stead very insulted because I think the approaches that were used were extremely reasonable, particularly for the time. But even today, I think that the approaches were fantastic. Now, the fact that they didn't find any life with the experiments that were sent on the Viking missions is not their fault. But I got to Ames somewhat after the Viking missions, but not that long after, and I got the sense that there was a little bit of an anti-biologist sentiment that you guys had a chance with Viking and, let's be honest, you failed, and so it's time for the geologists, the big boys, to get back in the game. And so I really thought I'd just be here for a year or 2, and then a whole lot of things happened, which I think really ignited what became astrobiology. And so as far as I'm concerned, part of it was discovery, increasing discovery, still going on today, of extrasolar planets. So the ancient Greeks suspected that there were planets other than those in our solar system, but now we know about them. We know about them by the thousands. We know about these solar systems and so on. And now I saw something the other day that they may be able to start to image moons of extrasolar planets. Phenomenal. So realizing that there were many, many other potential abodes for life, these huge advances in molecular biology, which allowed us to understand life in a far better way, and then synthetic biology, which I've been heavily involved in for the last 20
Mhm.
years. And also the discovery of life in many extreme environments that was really ignited to a large extent
Mhm.
by the work of Tom Brock at the end of the '70s and all his fantastic work in Yellowstone National Park, which made people realize just because water is boiling doesn't mean that it's devoid of life, or because it's ice or a salt crystal or all these things. So people started fanning out around the world and really looking for life in areas that up to then they assumed were not habitable. And so here you've got this expanded view of where you could have life on Earth. You had an expanded view of where life might exist in the solar system and then the universe as a whole, and then a deeper understanding of life on Earth. And so I think partly with all those things coming together, and then ALH 84001, the Mars meteorite, which had a whole suite of characteristics that one interpretation was that it was evidence of extinct life on Mars. All of a sudden, our administrator at the time, Dan Golden, realized that this could be something that was really important for NASA. And so he directed the foundation of this astrobiology program. And that was just when I was starting off as a civil servant. And I got really excited. Back to your original question, I got really excited because as an evolutionary biologist, I was raised with the whole sort of Herbert Spencer, nature red in tooth and claw, and you talked about competition. You didn't talk much about the environment. And all of a sudden, we were talking about the environment. I was going to extreme environments. We were talking about habitable planets and moons and all these things that were, just blowing my mind because it was, to me, evolutionary biology writ large. And I remember going to one of my administrators at the time and saying, "I will do anything to help this program." And of course, I was punished for saying that and asked to start a series of meetings, which are still going on today, the Astrobiology Science Conference, which is colloquially known as AbSciCon. So I got very, very excited on it about this whole potential as a biologist, as an evolutionary biologist, and I've just been very privileged to be part of this whole field, and to be honest, the founding as well.
And you talked about being an astrobiologist and working in this field for 20 plus years with NASA. And so what is the main focus of, you're on the cutting edge of ideas and exploring and practical applications of your theories and things like that. What are some of the theories that you're working on and the experiments that you're doing to propel, us into the future and expand our knowledge about where we're from, where we're going, and are we alone?
Great. Well, thanks for asking. So, what I've gotten particularly interested in is the environmental effects on life, because I think that's going to be key. If we thought that every other place in the universe was pretty much like San Francisco, which is, right there in the middle of what you would consider habitable, say, 60, 70 degrees Fahrenheit, 20 degrees Celsius, rains in the winter. It's very pleasant. We wouldn't be, concerned. But the fact is that there are very few places. In fact, we don't know any that's a complete overlap with the Earth. And when I say environment, it's not just temperature, it's pH and the solar insolation, the amount of radiation that we're getting, and gravity and all that. We need to understand how much life can go beyond what we're seeing, in my office. I'm not floating away, and it's not because I'm strapped to my chair. I've got 1G. We're all living in 1G environment, and I've got air to breathe. That's not a problem. I don't have a gas mask on. The temperature is very pleasant, so on and so forth. So I got interested, well, less in life in extreme environments, if you really want to know, but I was starting to go to extreme environments as a way to model early Earth, because once you start to hit high salt or high pH or low pH, a lot of, if not all, multicellular organisms drop out. So I thought this would be a great way to model ecosystems that should have been around literally billions of years ago. And so we were going to Yellowstone. We were going to for the high temperature, low pH, and we were going to Baja California for the high salt and so on. And then it sort of might be interesting to your viewers because this is really what life is all about. I would love to say I planned everything, but of course you don't plan everything. And I was asked by Nature to write a piece on life in extreme environments and search for life in the universe. And I wrote back to them with uncharacteristic modesty and said, I really don't do that. That's not my field. I'm probably not the right person for it. And they wrote back in their own inscrutable way and said, "It's okay. We like the way your brain works." It's like, but I know what they meant was that I didn't have really a horse in the race, because I was not a specialist in that who was only going to pump up a high temperature Archean that I'd been working on for 30 years or something like that. I could stand back a little bit and look at it a little more dispassionately. And so the result is this thing was published in 2000, 2001, whatever that was, and then everyone started to ask me to talk about that. And so I've given innumerable lectures about life in extreme environments and search for life in the universe, and therefore got interested in that and the environmental aspects, even of the origin of life. So you asked what we're doing right now. My lab has been heavily involved in founding a program in synthetic biology for the agency. And so what we've done is started to combine the two. So The question is, we can go out into nature and look for organisms living at high pH in the Rift Valley in Kenya. We can look for the low pH in Yellowstone. We can look for the high temperature in a geyser. We can look for the low temperature in the Antarctic or under ice or whatever. We can do all these things. That's fine. But I firmly believe that not only can life go beyond some of these extremes and may have
Hmm.
in the past, even on planet Earth, but the environments are no longer there, that we don't necessarily have all the combinations. So no one lives in a pH or a temperature or a gravity regime. You have all these things happening at once. And life may not have the opportunity to test all these combinations on the Earth today or even ever. And so what my lab's trying to do is make synthetic extremophiles to try to push the bounds of what life is living in today to get a better idea of what life, even as we know it on the Earth, might be able to do, some of the habitats it might be able to live in. So I always sort of joke, what if an astronomer finds a planet and says, well, Lynn, it would be great for life, but you tell me that 121°C is the highest temperature for life, and I estimate that this average is about 130 or 140. Otherwise, it would be perfect. Do I have to cross it off the list? And I always joke, I hate to see an astronomer cry. And so I hand them a tissue paper and I said, let me see if I can make something that could live under those conditions. And I really think that we have a better chance of pushing those bounds in the lab right now with the technologies that we have than trying to have a space mission outside of our solar system or even the outer reaches of the solar system and find something. So that's what I'm doing. Some of my lab calls it synthetic extremophiles. The original students who started working on it called it the Hell Cell Project, and I think that's a much better name. So it is the Hell Cell Project.
I was watching one of your lectures that you did a number of years ago online in preparation for this
Reactors are
interview,
well
and I
below
found it
zero,
extremely
they
fascinating. And you
just
just kind
simply
of break it
maintain their
down
current
into,
environment.
you talked about
Similarly, as you
DNA and
go
then
up in
RNA and then
temperature,
creating
a lot of
proteins
the
in this kind of
eukaryotes,
circular,
organisms like us, drop out. And
evolution
eventually, we'll
of
only
just
have life
life and
here in
building
our
off of that.
at
But
the
out
very
in space,
highest
there's no
temperatures where we
RNA,
have
right? But you say like
archaea.
amino acids can still thrive. You've found that maybe in meteorite sections and things like that. Can you talk about some of this extreme environments and where there is signs of some of these elements that do bring life forward?
So to have life originate, we need certain building blocks. Life doesn't just start with CO2 and say, here, let me try to put it together and make something. And so you think, well, this is amazing that we had these here. We know that there were certainly amino acids. In fact, the ones that we use today, there are other amino acids that we don't tend to use, but even the ones that we use can be found in meteorites coming from space and comets and being synthesized in prebiotic scenarios, like hot springs and so on. You may remember the Urey Miller experiments, Stanley Miller's work when he was working for Harold Urey, where he was set up a you know apparatus that looked like sort of the stereotype of the mad scientist, where he took some of the inorganic molecules like methane and nitrogen and so on, and bubbled and boiled and recondensed and so on, and they were able to get amino acids. Now, some of the inputs we don't think now were necessarily the prominent ones on early Earth, but it showed that you could start with inorganic compounds and end up with some of the building blocks for life. We know that some of the other ones, like nucleobases, are also found in the interstellar medium or comets or whatever, or can be made in simulations of the interstellar medium. So that really gets into a field that's not mine, but I'm fascinated with, and that's the whole idea of interstellar chemistry. So probably a lot of people in your audience remember taking chemistry. And,
Yeah,
we
yeah.
can't,
Not very
can't,
good at it. Sorry.
can't say it was my best subject either. But then I think it's partly how it's taught, because there are all sorts of aspects of chemistry we don't think about, and one of them is interstellar chemistry. What is going on between the stars? Now,
Mm.
people in the field tell me 50 years ago, if you walked into a meeting and said that there was anything there, I mean, a single atom, you would have been laughed off the stage. And then it's like, well, we found some hydrogen and we found some nitrogen. And now there are all sorts of other things that they found. And then, again, as I say, you find these building blocks of life on comets, on meteorites, in simulations, the interstellar medium. And what's interesting is there's a very good overlap with what life uses on Earth. And so I've come to the conclusion, not because I am not wildly imaginative or anything else, but because I think the universe is trying to tell us something, that the language of life that we use on planet Earth may have a certain universality to it. It
Hmm.
may if there's life elsewhere, it may be basically the same language, and so I find that sort of fascinating that some student around Alpha Centauri or who knows where may be using a similar sort of biochem book when they're studying for their exams that we use on planet Earth. And if that's true, that gets us a long way towards being able to find life elsewhere. If there's certain building blocks that are the same, we could also go into the idea of using liquid water as a solvent, which has a huge number of advantages. And then you're really talking about a much more constrained system that you're looking for. And I think that that's, absolutely stunning.
So you mentioned how, the possibility of the same elements that make up life here on Earth could possibly exist in all areas of the universe and beyond. Um, what about the concept of, follow the water? I've heard that in science, especially in something that you were doing in astrobiology. It's just like, where can we find water, traces of water, chances for water, and is that important in what you're doing?
Okay, so the whole water thing is because the assumption is if you have, well, we were talking about life being amino acids and so on. A
Mhm.
shorthand way to say this as a scientist is it's all based on organic carbon. So,
Okay.
we had CO2, carbon monoxide, diamonds, I'm looking at my ring, are inorganic forms of carbon. Organic is basically carbon with hydrogen. That's why I sort of laugh at the organic section of the grocery store because if that's true, then the inorganic section should just be piles of diamonds and tanks of CO2, which I don't know why your grocery store buyers don't have that. Anyway,
I
be that
love
as it
that, yeah.
may, you then need a solvent. And if you start to think of some place like Titan, where there's lots of organic molecules, the solvent there is liquid ethane, methane. And you think, well, maybe you could form life that way. But I think there's a really good reason to think that it's probably going to be water in most circumstances. I have to say, years ago, I was asked to talk to the water board in the Netherlands for their annual meeting. I think I was sort of their after lunch entertainment. So I came up with like 26 reasons why you want to use water. But one of the big things is that it's got great chemical properties in terms of having a positive charge and negative charge. It you can end up with hydroxyl radicals and hydrogen ions in solution, which has a lot of advantages for chemistry going on. Um, but I think actually one of the two big things are the fact that it's liquid at a fairly high temperature compared to things like ethane and methane and so on. And so reactions can go at a reasonable rate. So you think about think about how fast you move when it's really cold. Things metabolism slows down. Imagine if you were living in a place colder than your freezer that was, the temperature of literally of liquid nitrogen. Reactions don't go that fast. Biochemical reactions go very slowly. And so my concern is if you're using a solvent like that, the reactions may be so slow that you end up having whatever molecule you're making breaking back down before you can go anywhere. So water is liquid at a much, much higher temperature between, of course, pure water between 0 and 100 Celsius. So that's a really nice warm range compared to these other alternatives like ethane and methane and so on. So that's one. And the other thing is it's all over the place in our solar system and our universe. I sometimes show an artist rendition of the early solar system forming based on the formation of another solar system that had been observed. And you see this giant, like gaseous blue ring. And what was the result of that? Well, we don't have water on Mercury. Venus has some in the
Hmm.
clouds. We've got plenty on the Earth. Moon had possibly has a little trapped in it. Mars certainly does. Look at the asteroid belt. I'm a little out of order now.
Yeah.
And then you start to get to places like Jupiter. Okay, Jupiter doesn't, but it's got a couple of icy moons that are covered with
Yeah.
ice and have liquid water underneath. Ditto
Right.
with Saturn. Now we think Pluto's got ice on it. I mean, it goes
Hmm.
on and on and on. I mean, comets are ice. So water, whether it's solid, liquid, or in gas form, is all over our solar system. And from what we can tell, all over the universe. So it's all over the place. So it's a great solvent for chemical reasons. It's a great solvent because of the temperature regime, and it's all over the place. So, it makes one think that that's probably a great choice for life.
There's lots of exploration that's been happening on Mars, and the whole world is wrapped to it. They're really, and that's what I really like about it, that an average science curious person like me can even be pulled into the
Oh, God.
excitement of
Oh,
what's being discovered.
I
I'm
remember a
sorry, what?
couple of years ago that the British mission, the Beagle 2, ended up being lost on the surface of Mars. And it was around Christmas time. And I think I was wearing my NASA jacket when I was visiting my parents. And people came up to me on the street like it was a death in the family. We're so sorry about the Beagle. Which is
Yeah.
personal, that was British. But I mean,
Yeah.
that's the kind of personal feeling I think people have about space, and I
Yeah.
don't know about you, I was a kid when Neil Armstrong first stepped on the moon and
Yes.
Buzz Aldrin, and, the world stopped for this, and we
Yeah.
were all one, we were all humanity together.
I was the kid that ran outside to look at the moon and then ran back inside to watch him on TV, then ran back outside and said, "Oh my god, there's a guy up there. There's a guy up there." And I was just my mind was blown for sure.
Yep.
Absolutely. But my question about Mars was obviously lots of exploration, people are into it. What evidence are you finding or discovering or talking about in regards to life there on Mars and the potentiality of that? And what signs are you specifically looking for in this field of astrobiology on Mars?
So, first of all, there's sort of a strategic answer, and then there's the scientific answer. The strategic answer, and I think we learned this from the Viking missions, is we don't talk about having a mission to look for life because the feeling is going to be if you don't find life, you were a failure, you wasted taxpayer money, and so on. So you don't frame it that you're looking for life, you're looking for habitable environments or whatever, so that you will get something no matter what. It's not going to be a binary, yes, we were successful, we found life versus we were total failures. So, we're gonna look around. I think strategically it is not in our best interest to say we are going to look for life. Yeah, we are, but we're gonna get a lot of other information.
Yeah, of
So in
course. Yeah.
terms of right. So I think the story is that the conditions for life to arise on the Earth should have been there on Mars. In fact, potentially even earlier on Mars than on the Earth because it's a smaller planet, it cooled down faster, and so on. Lot of the same should have had the same inventory of biomolecules. We know that there was water. We know it was warmer at one point. We talk about warm and wet. Who knows if there were oceans or liquid or it was sort of crunchy ice but it was warmer than it is today. There was some kind of atmosphere, and so on. So the conditions were similar, and life is certainly possible under those conditions because it happened on the Earth. Is it likely? It's possible. Is it likely? Is it probable? Is it inevitable under those conditions? That's up for debate. But we know that it was at least possible. Now, what's happened since then is the poor little Mars lost its atmosphere to a large extent, and it got a lot colder and so on. But the water inventory is still there, and there certainly is an overlap between the environments that we find life on Earth and the environments that we see on Mars. Even today, I could find you an organism that could live on Mars. Now, I don't know if
Hmm.
it's be inviting you over for a Halloween party. Is it going to be thriving? It's another matter. But I think that particularly if we start looking at microenvironments beneath the surface, beneath the polar ice cap, I'm actually very touched. I work with geologists a certain amount of time, starting another project with geologists, and they're very thoughtful. They want to find you a global ocean. And I keep telling them, I don't need a global ocean. I'm a microbiologist. For a microbe, 1 milliliter of water is an eternity. That is they wouldn't know what to do with a Mars-sized ocean. And so then they say, "Oh, that's all you want?" I said, "Yes, just give me a milliliter, maybe even, a tenth of a milliliter of liquid water as a fluid inclusion." And they was, "Oh, we can find you that." It's like, well, then, game's on.
Wow. That's
So
exciting. That's
I
exciting.
that's what I think is that we really need to be focusing on the microenvironments that are relatively shielded from radiation that is going to destroy the biomolecules. Anyway, that's where I would go. That's where I would look. We have done some work with organisms that live in an evaporated crust, so salt crusts. I know they can survive for long periods of time, be protected from radiation. But again, at some point, they're going to need liquid water. They're going to need to, you know, divide and clean up their damaged DNA from the radiation, and all that sort of stuff. So what you ideally want is at least some periods of time where there is some liquid water, but it may not have to be constant. I mean, I'm live in Northern California. There is so much excitement because there's a 70% chance of rain tonight. It
Oh,
literally, I
nice.
mean,
Fantastic. Yeah.
yeah. At our house, it did actually rain this week, but where I am at NASA, it has literally not rained since last April. And
Wow.
obviously, there are
Yeah.
probably things
Yeah.
surviving. I'm looking out the window, I see the trees, I see the insects and the birds and so on. So we know that we can deal with episodic periods of not having liquid water, or at least rain. What can we actually survive with, and how much darkness, and all these things that again gets back into what I'm talking now about with extremophiles.
What do you think is going to be the next big discovery? Or let me rephrase the question. What do you think could possibly be the biggest discoveries in the field of astrobiology in the next 10 years? What are you excited about on the horizon?
Well, I know what the biggest one would be is to find evidence of life elsewhere, and if you really want the icing on the cake, that was a separate origin than the life on Earth. How would we know it was a separate origin?
Hmm.
Well, all life on Earth, for example, uses right-handed sugars and left-handed amino acids. So all of our proteins, with a few little exceptions like a few antibiotics and so on, but basically all the proteins that we make with our ribosomes use left-handed amino acids. But why? Maybe it was something that sort of locked in early in evolution. If we find organisms that are predominantly right-handed amino acids, so mirror life, or left-handed sugars, or use different amino acids, because I'm sure they're going to use amino acids because they're all over the place. That one is sort of like a no-brainer to use proteins. Um, other sorts of molecules maybe that we don't use as much. Maybe instead of DNA and RNA, they have some other kind of genetic system. Um, Maybe they don't actually use water. Maybe my arguments are wrong. So there's something that's fundamentally different than the commonality of life on Earth. That would be so exciting. And I just talk about look at the look at the people who work on extrasolar planets. There was a time that we did not know for sure of any other extrasolar planets. And I went to a meeting that was the anniversary of the discovery of the first one. I mean, could you imagine that discovery? So suddenly, instead of having zero extrasolar planets, you had one, and now we get them by the hundreds and the thousands after Kepler and then Tesla and all these other missions that are up there.
And
But
could you explain just extrasolar planets? Could you
yeah,
just define what that is for the
sure,
average person?
absolutely. A planet that does not orbit our sun, so it orbits someone else's sun. So it's an
Great.
extra solar, it's beyond our solar, regime. So we as biologists, are still in that point where before they had discovered a planet around another star. We only have one data point for life. Now, there's an amazing diversity of life, but all life uses the same operating system. We're using the same ribosomes, basically. We're using the same left-handed set of amino acids and right-handed sugars. And yes, there are a few decorative elements. There are a few little things that are different. They're dinoflagellates that use 5-hydroxymethyl instead of thymine, and that probably means nothing to you. But that's a fundamental
It's over my head. It's just over my head.
right, and dinoflagellates are a wonderful group that I did my master's on, algae, and unfortunately, they have a bad rep because they also cause red tide, but not all of them do. Anyway, they use a different base. Okay, there are little oddities like that. And obviously, we have a huge morphological and diversity of life on Earth, whether you're looking at a kangaroo or a dinoflagellate or whatever. That goes without saying. But it is fundamentally working on the same set of biomolecules and the same operating systems and so on. If we could find even one other example, maybe we would start to discover that life on Earth is not the only way to do it. And
Mm.
maybe if we started then having 100 or 1,000 independent origins of life, like
Mhm.
these astronomers have all these extrasolar planets, what if we had 10,000 examples of life and we could say, oh, only 3% do it the way we do it on the Earth, and 70% that way. So to me, the most exciting thing that could happen would be to find evidence of life elsewhere. And then, as I said, the icing on the cake would be to discover that it was an independent origin. Whether that happens in the next 10 years or not, I don't know. But conversely, to me, the greatest tragedy would be if we go to a body, a planet, say Mars, and there was life there and we contaminate it with Earth life to the point that we cannot recognize what is what. And so, therefore, we have lost the opportunity to make this phenomenal discovery. That would be a real tragedy.
So there must be a lot of real ethical discussions and arguments about astrobiology and the purpose and the mission with the point that you just made. My gosh, we're assuming that everything is perfect on Earth, but it could be disastrous for some other ecosystem on some other planet somewhere.
Right. So, I mean, when we go to Mars, we're gonna be the invasive species. You think of it that
Right.
way.
You talked about synthetic biology and you're leading the charge in that area and you're very, very excited about it. Can you give us a practical example of something that you would create synthetically and how that applies? What would you do with it and how do you put it into practice, so to speak, out there in space, and what would it mean?
Okay. I'll give you an example that's probably closer to what we've been discussing right now, and that is one that we've just gotten funded on detoxifying perchlorates. So, probably a lot of your listeners know that there are perchlorates in the water on Mars, and it's at a level that would be toxic for humans. So, obviously, that means that we can't just go to Mars, melt some water, and drink it. We have
Right.
serious lethality problems. Turns out so we could build some fancy machine to get rid of the perchlorates, but then you have to launch it and have it work off planet. It turns out there are a couple of organisms on the Earth that have figured out how to change perchlorates through a couple of steps into chlorine and oxygen. No problem then, this is great. You've got half a table salt and you got, or disinfectant, and you've got more oxygen to breathe. So that would be ideal. The problem is the organisms that can do this are not ones that you really can count on for a space mission. So what we're doing in my lab right now is a project where we're taking out some of these genes, these capabilities from the organisms that can detoxify perchlorates, and putting them in an organism that we know is particularly good in space, Bacillus subtilis, and then being able to develop a system where that is the core of it. So you run water in these bacillus now who are engineered to take up the perchlorates and detoxify them, do that, and then you've got clean drinking water for the astronauts. That's being led by Garrett Roberts Kingman in my lab. We also have a project where we are developing an astropharmacy. So many drugs are only made transgenically, so I'm challenging my people to take something the size of a cell phone, and you bring up a library of cells that are programmed to make different drugs, and you activate them when you need them, and in 24 hours, you've saved an astronaut's life. So those are examples. We just had a patent issued in biomining where we've taken taken advantage of the fact that there are many biomolecules in your body and mine that bind metals with unbelievable specificity, much better than anything else out there mechanically. So, as I like to say, when you woke up this morning, your hemoglobin didn't say, "Gosh, I wonder what it would be like to bind cobalt today. Wouldn't that be fun?" No, no, no. It doesn't work that way. It's iron all day, every day, or you're dead.
Hmm.
And so, what if we could take that kind of radical specificity and use that as a way to extract and separate metals? And so, that's what the patent that we just had issued is on the idea of taking short proteins that are very specific in binding a metal, and the other end engineering them so that they will bind to the outside of fungal mycelium. Have it all over my desk. Oh, here's some. Um, Example of some fungal mycelium. You
All
could
over your desk. There it
yeah,
is. Yeah.
you could bind these little, proteins to this, and so now you've got a filter that you've grown where you can pull out whatever metal you need to pull out. So you can see I'm very bullish on that. So there are a whole lot of things, but then back to the whole synthetic extremophiles, that's a great way to help understand what the limits are for life, but it'll also be a way to enable astronauts to be able to live off planet because we're already talking about having biological based fermentation units, certainly food, materials. There are all sorts of things that you can make biologically. I'm wearing things right now that are made of wool and cotton and leather and all those sorts of things. There are ways that we're going to be able to take advantage of these capabilities of life off planet. But say you can grow the cells that are making these at a temperature that's a little closer to what you're getting on Mars or the moon, or a little, able to tolerate a little higher radiation or whatever, that will increase your efficiency. So I think the Health Cell project is, I hate to use the expression, but dual use, both for the astrobiology and for enabling humans off planet.
Last question for you, and I could sit here and talk to you for another 5 hours because I just love all this stuff. And thank you so much for your time, Dr.
Oh,
Rothschild.
my
But
pleasure. My pleasure.
we're in the world of AI. We're in the world of AI technology. Where do you see AI playing a role? Like you mentioned, interstellar mediums being created for some of your experiments. What do you see AI doing in the future to help you along with astrobiology in your work?
Well, I mean, from a trivial sense, like everyone else, when I Google something, all of a sudden I get an AI generated summary now, which saves a huge amount of time. But really, the field of biology, particularly synthetic biology, has been using what's been called bioinformatics for years. So I finally started asking people, where's the line between bioinformatics and AI? And they sort of giggle and say, well, actually, there is no line. So we've been using the power of computation and deep learning, whether it's recognizing the difference between a cell and a contaminating particle or the size of a cell, or being able to scan literally millions of genes from the diversity of life on Earth to understand the commonality or where the radiation resistant gene may lie. So I think that is something that we've already been using, but using it with different terms. We've been calling it bioinformatics. Now, I have not been heavily in that field personally, just because I'm been learning a lot of new things in my life, and I cover a lot of fields, and I've decided that's just one step too far. So the smart thing to do is get really clever students and postdocs in your lab who do know these things and can move the whole thing forward and say, gosh, when we start to do this, it's going to really move it forward. So one really concrete example is the biomining project I was telling you about. Now, nature has evolved a lot of peptides, short proteins that bind different metals. But there are many other possibilities out there that either nature has not evolved or they evolved it in the past and we can't recover it because it went extinct with the dinosaurs or before.
Hmm.
And so, right now, that field of computational protein modeling is huge. And so the ability to say, all right, design a protein that will bind, say, platinum, but not palladium, would be phenomenally useful. So I think that, I'm at the point that I understand where it can start to go. I will not be doing that myself, but I think that it will be providing yet another very powerful tool for the field.
Dr. Lynn Rothschild, thank you so much for your time and your brilliance. I mean, look at all these notes. All these questions. I didn't even get a chance to ask you pages and pages of questions. So you have to promise to come back on Ignition Sequence.
It would be my honor. This has been so much fun.
Thank you so much. Have a great day. And we look forward to speaking with you again very, very soon.
Absolutely.
Ignition Sequence is produced by Accelerator Media, a nonprofit organization dedicated to inspiring a lifelong pursuit of knowledge. Join us every week as we dive into the science, the stories, and the extraordinary journeys that challenge our understanding of the world. Subscribe now and ignite your curiosity with us. Ignition Sequence. Listen, learn, repeat.